So I've gotten a few questions about homework number 9, so I'm going to explain a few ways to use the pumping lemma for context-free languages in terms of the questions we have for homework 9. So we are familiar with the pumping lemma from earlier in the semester, but for the context-free language application, you're going to want to look at page 19 of Dr. Choi's notes. And for the pumping lemma, what we are going to use is these 5 postulates, which is the string omega has to be greater than or equal to p, the pumping length. Omega, or w, the string, is going to be composed of the substring u, v, x, y, z. The length, written here in terms of magnitude, of v, x, y is going to be less than or equal to the pumping length. And then the magnitude of just v and y is going to be greater than or equal to the length 1. And then for all I greater than or equal to 0, sorry, the resolution is really bad. So for all I greater than or equal to 0, u, vi, x, yi, z is going to be an element of the language L. So any number I going from 0 to any positive integer. So if we look at question D, I believe, on the homework, we have a language L, which is composed of a string of A's of length r times s, where r and s are both prime numbers. So we're going to postulate we have a string omega, which is equal to a to the 2q, so 2 times q. 2 in this case is r and is a prime number, and q in this case is s and is a prime number. And we're going to assume omega is an element of the language. So we're going to say that q is a prime number larger than the pumping length p. So we can also define our substring s, or it could be omega, I wrote s this time, as being equal to u, v, x, y, z. Where, because of our pumping lemma prerequisites, vxy is less than or equal to the pumping length p, so the magnitude of vxy, and the magnitude of vy alone is greater than or equal to 1. So this is trivial, but vxy can only contain a's because our string is only made up of a's. And then the important part is we're going to utilize postulate 5, where for all I greater than or equal to 0, u, v of I, x, y of I, z is an element of the language, so any positive integer or 0 can occupy this value of I, and this needs to hold true. So we're going to let I equal this value, 2 times q plus 1. And if we add that to our string, we will result in u, v, 2q plus 1, x, y, 2q plus 1, z. And that equals a to the 2q plus 2q alpha plus 2q beta. It's very important to understand what this math means. So remember, v to the 2q plus 1, this is not an exponential operation here. This is, we have 2q plus 1 v strings. So whatever v is, whatever the string v is made up of, however many a's make up v, we're going to have 2q plus 1 of them. Then we're going to have the string x, then we're going to have the string y, which is going to be 2q plus 1, and then we're going to have z. Now why we can say from this that we have 2q plus 2q alpha plus 2q beta a's is because we know the original string, this string here, u, v, x, y, z, is 2q long. It's a times 2q. Sorry, it's not, it's 2q a's. And here, in this definition, we still have u, v, x, y, z because we have v 2q plus 1. So this could be distributed as v 2q v x y 2q y z. Because remember, this isn't an exponential operation. This is simply stating that we have 2q plus 1 v's. And v is some arbitrary number of a's. So why we can write this in this form is because we have u, v, because we have 1 v, x, y, we have 1 y, z, so we have 2 QA's. So that's coming from simply the fact that we know that the original omega has 2 QA's, and then we get these other two terms, 2q alpha plus 2q beta, because we're adding an additional 2q to v. We're adding an additional 2qv's, and we're adding an additional 2qy's, and the alpha is the arbitrary length of v, and the beta is the arbitrary length of y. So that's where we get our knowledge of how many a's we have. This is the most important part to understand. It's the central part of the proof. Once we have that, we can do some redistribution of the values, pull the 2q out, where we're left with 1 plus alpha plus beta, and now we have our contradiction, which is the following. 2 times q cannot be a prime number, because 2 times any prime number is not a prime. And we know this is going to fail because now we've put this in the form ARS. A times, sorry, not times, do not make that mistake. You have R times S A's. So if R was 1 and S was 2, that wouldn't be the case. R would have to be 2 and S would have to be 3 because they both have 3 primes. Then we'd have 6 A's. It's not A to the 6. It's 6 A's if R was 2 and S was 3. So this 2q here is substituting for our R. So R needs to be prime because it's this part of the R times S, but we know 2 times q cannot be prime. Therefore, contradiction. L is not a context-free language. 1 plus alpha plus beta could be prime. We have no knowledge of that. Alpha and beta are just arbitrary numbers. But the trick to this whole problem was figuring out how to write the total number of A's in terms of this format from this knowledge, so then we could then create this contradiction by multiplying 2 times a prime number, which we know cannot be prime. One other question we can go over is A. So we still have our same pumping lemma requirements for context-free language. For the string omega, greater in length than the pumping length, omega is composed of the substring u, v, x, y, z. The length of vxy is less than or equal to the pumping length p, and the length of vy is greater than or equal to 1. And for all I greater than or equal to 0, u, vi, x, y, I, z has to be an element of L. So here we go. Here's A. The language is 0n, 1n, 2n, where n is greater than or equal to 0. So we're going to create our string omega, 0p, 1p, 2p. So that means p0s, p1s, then p2s, which is going to be equal to u, v, x, y, z. This follows the rules of the language, so this is an element of the language. We can look at the two cases we're going to have. So our string is going to be some number of zeros, followed by some number of ones, followed by some number of twos. And what's important here is that we know that vxy has to be less than or equal to the pumping length. It's one of the rules. That means that Vxy, this center of the string, can only sit in one of 5 positions. It can sit right here, where Vxy has to be less than P, so it can be all zeros, it could be all ones, and it could be all twos. It's important. This is what limits the number of cases. It's because we set our string to be P zeros. It could be any length n, but we set it to be the pumping length, and this Vxy has to be less than the pumping length. So it couldn't be 0 through 1. That would be too long. However, there's 2 other places that Vxy can sit. It can sit and straddle 0, 1, or it can sit and straddle 1, 2. You could write all these out, but they're 2 fundamental cases, so that's why I wrote them, case 1 and case 2. You could write them all on your homework, on your test, but if you get at the core of what are the fundamental different cases, you're fine. Case 1, Vxy contains only zeros. This would be true if it contained only ones or it contained only twos. If you apply Rule 5, where for any I this has to be an element of the language, you would get U, V2, X, Y2, Z. This would not be an element of L, because your 2 for the Y's would only be zeros. So you would end up adding more zeros to your string, but no more ones or twos, which would result in a string that didn't have an even number of zeros, ones, and twos. You'd have more zeros than you'd had 1 and 2s. So therefore, it would not be part of the language. Case 2 would also fail by this same logic, but case 2 would also have to deal with the fact that Vxy, which sits on the border, for one example, contains zeros and ones, because it sits on the border. So if you applied the final rule and made I equal to 2, you would have U, V2, X, Y2, Z. This would not be an element of L because it would create a reversal of zeros and ones, because you would have in the V or in the Y, you would potentially have X, you would have zeros, and then in the Y, you would also have potentially ones. And even if the X value sat exactly on the middle point of 0, and if X sat on the last 0 and Y sat on the first 1, you would still get an additional zeros created and additional ones created, which would result in having more zeros and ones than you had twos. So it would be covered under the first case. And you would also have the issue of if V or Y crossed over between 0 and 1, you would get a string that was out of order, where 0 and 1 would repeat. So you would have a string 0, 0, 0, 1, 0, 1, 0, 0, sorry, 0, 0, 0, 1, 0, 1, 1, 1, 1, 2, so on and so forth. And that wouldn't be in the correct order, which would also mean it wasn't an L. So that's the proof for A. There's a lot more you can write out, but this is the very bare bones.